What's up, yo? I'm gonna try something new. I'll let you watch me freak out as I start yelling and screaming at you. I don't know, maybe it'll make it more entertaining. Because that's so exciting. Let's get it. More dot product, more fun shit. There's a definition we got from before. Makes tons of sense, huh? And now, we're into the rules. What's up with our rules? Shit. Like U, V, and W be vectors in the plane or in space? What the F? We're in space? And let C be a scalar? There's just a bunch of shit written down. Let's get out of here. Let's go over here. Let's look at some mellow shit. We know how to dot now, don't we? If you just watched the last one, I mean, really, you just gotta watch it. Try one, and you're like, shit, you can dot vectors. So why don't we go through and just solve a few of these? I got a bunch of crap. No, other shit. Let's go through. Maybe we'll learn something. All right, so if we're gonna dot two vectors together, what is that gonna be? We're gonna go take the horizontal or the I hat component. We're gonna multiply that shit together. So the 3 times that -5. And then we're gonna add it to, yeah, you guessed it, whatever's gonna happen here with our vertical components. The 4 times the 12. And what do we get? We get -15 plus 48. Oh shit, is where I typically ask class to help me out. What's that, 33? Fascinating. Look at that number we just got. It's pretty impressive. It's positive, so we know that the angle between the two vectors is actually less than 90 degrees, but yeah, whatever. Oh, let's go do number 2. Let's jump into this tough one. So now it's W dotted with vector V. Okay, well, we better take our horizontal components and dot them together. Oh, it's going to make a big difference down here. -5 times +3, right? Because these two things are so different when you turn them around, huh? No, it's the same shit. Yeah. Cool, now we're going to do the same thing with our other ones. Now we're going to oh, well, it's the W vector. We better take 12, huh? Multiply the 12 times the 4, and, well, shit, it's still -15 plus 48. The damn answer, 33. And what that's doing is it's just showing, shit, go away. It's just showing it's commutative. It means if you dot it, doesn't matter which direction you're coming at it. It's no big deal. The next one says that you have a 0 vector. If you take the 0 vector and you dot it with the V vector, it means all the components are 0. So everything you multiply is 0. When you add 0 and 0, I'm pretty sure you get 0, right? But it's not a vector. It's just a frickin' number. Remember that. Dot products are just the numbers. Nah. I'll start yelling. I can feel it. All right. And now we're going to go to number 3, which is asking us, let's just go dot V with V. Well, let's dot V with V. So it means let's take that 3, and we gotta dot it with the other vector, which is V, which is, oh, it's still 3. And now let's take our so we better dot it 4 with 4. We gotta multiply those together, 4 with 4. So isn't that 3 squared plus 4 squared? So what's that, 9 plus 16? So isn't this equal to 25? And again, fascinating. But something seems familiar about what we just did there. Let's dot W with W. Let's make sure we got this pattern down. So that's saying, well, we better take our -5, and we better do -5 times -5, or I think that's called -5 squared. No shit, I put an equal sign. No equal sign. We need a plus sign in between these suckers. And what are we going to put in? Oh, yeah, that's right. We're going to have to put in our vertical component of W. That's 12 and 12. So I'm pretty sure that's called 12 squared, but who gives a shit? So this looks like, I don't know, 25 plus 144. I think that thing's equal to 169. You're like, cool, we're getting numbers. How amazing could that ever be, you know? And now you want me just to go find the magnitudes, huh? We'll laugh at. Let's go up here. Let's go find the magnitude of vector V. Now what do we do here? That's the square root of its component squared, right? So that's going to be the 3 squared plus the 4 squared. The 3 squared plus the 4 squared. The 3 squared plus the 4 squared, huh? Which will give us that square root of 25. There might be something to do with each other in here, but whatever, we found an answer. Now we go over to number 6. I'm like, all right, well, let's go find the magnitude of vector W. So that means, all right, let's go take our components. Let's go square them up, add them up. So -5 squared plus 12 squared. We get, well, that's 25 plus 144. I swear we've said 25 plus 144 before. So that's the square root of 169. Oh, weird. Weird. Probably a coincidence, huh? And then we find out that the magnitude of vector W is 13. Weird. So it almost seems like W dotted with W, right? That 169 is just equal to the magnitude of W squared. You know, 13 squared? Because isn't the same thing with vector V dotted with vector V? We got 25. And then we got that the magnitude of vector V was just 5. And I think we have to square this shit up. Yeah, that's this property right here. So I figured probably better show you rather than just like really cuz. And then 3 and 5. Don't stress about 3 and 5. I'm gonna do a proof. Remember, that's the one you're gonna want to watch. You're definitely gonna want to watch that one. But you'll have a quiz inside of there. You're gonna want to watch, and I'll just drop it somewhere quickly and in there. So yeah, good shit. Good shit. Little properties of the dot product, huh? So we played around with it. We just had some games with it. You don't need to know all these things, but it'd be kind of nice to shortcut some stuff. So when you dot something with itself, you just get its magnitude squared. Interesting. I'm going to use that a little bit on this next proof that I do. So we'll get into something like this later. This will be our next piece. We're going to try and find angles between two vectors. How freaking fascinating is that? Cool. See ya.